What I'd like to do now is I'd like to look at how we solve problems involving the volume of similar shapes. We already know that the area scale factor is the square of the length scale factor. If instead we consider a three-dimensional shape, and I've drawn two cubes here because cubes, similarly to spheres, are always similar, mathematically anyway, you can see that each of the lengths has been multiplied by 2. So our length scale factor is 2. If instead we consider the volume of the shapes, we've got the volume for the smaller shape being 2 times 2 times 2, which is 8. The volume for the larger shape being 4 times 4 times 4, which is 64. Now that tells me that the volume scale factor is 64 divided by 8, which is 8. I have no doubt you've already noticed that that means that it's 2 cubed, which gives us then that the volume scale factor is equal to the length scale factor, or the linear scale factor, cubed. Volume scale factor equals length scale factor cubed. And equally, the length scale factor is the cube root of the volume scale factor. Now, the reason that this works is because each of the lengths has been multiplied by the length scale factor. So when you're thinking about the volume, because you're multiplying the three lengths together, you've got length scale factor involved here, times the length scale factor involved here, times the length scale factor involved here. So it makes sense that it's got the length scale factor cubed for the volume scale factor. Now, sometimes your problems don't necessarily just involve the length scale factor and the volume scale factor. If you look at this question here, for example, it says the area of the bases of two similar glasses, so they're similar, that's important, are in the ratio 4 to 25. Find the ratio of their volumes. Now, we don't currently have a link between the area scale factor and the volume scale factor. So what we've got to do is we've got to say we know the areas are in the ratio 4 to 25. I can't go straight to the volumes, but I know that the area scale factor is linked to the length scale factor. So why don't I think about what's happening to the lengths? So the lengths will then be in the ratio the square root of 4 to the square root of 25, which would give us 2 to 5, which would end up giving us a length scale factor of 2.5 if you actually needed to find the scale factor. The volumes, therefore, will be volume scale factor is length scale factor cubed. So we're going to cube these, 2 cubed to 5 cubed, which would give us 8 to 125. And if you want to think of it in terms of the scale factor itself, what you would have is the volume scale factor would be 125 over 8, which is 5 over 2 cubed. So it all follows. So that's an example linking the area and the volume together. What I'd like to do is look at two other examples. So let me move those across. And if we look at example 2 first, your keyword that you want to be looking for when you're doing these sorts of problems is similar. Or you need to look at the shapes of the objects to see if they can possibly be similar. As soon as you see similar or mathematically similar written in a problem, that tells you you're thinking about length, area and volume scale factors. I tend to think that it tells me to draw a diagram as well. Even though these are three-dimensional shapes, I would personally just draw two shapes. If you want to put handles on them because they're jugs, you go for it, you don't have to. And what we've got is we know that the height of the smaller shape is 4 centimetres. The height of the larger shape is 6 centimetres. We know that they're similar. Now them being similar tells me that to go from the smaller to the larger, I will multiply by the scale factor, whether it's the length scale factor, the area scale factor, or the volume scale factor, it really makes no difference. To go from the larger to the smaller, I'm going to divide by the scale factor. Now, so that's what just the first sentence has told me. If I look at it then, it says the capacity of the smaller jug. Capacity, remember, is the amount that an object can hold. Volume is the amount of space it takes up. The capacity is the amount that it can hold, so it's actually talking about the volume of the interior of the shape. So it's still volume. We've got here, my green is not working very well. We've got 50 centimetres cubed. So what I've got to do is I need, in order to find the capacity or the volume of the inside of the larger jug, I need the volume scale factor. But at the moment I don't have it. What I have is I have that the length scale factor, which for the sake of argument I'm going to put LSF because it's quicker, is 6 divided by 4, which is 3/2. That allows me to say that the volume scale factor is going to be that cubed. Now remember from your work on indices that if you are going to cube a fraction, what you're going to do is you're going to cube the numerator, cube the denominator separately. So that gives me 27/8. I can then say, therefore, the volume, or the larger volume, is going to be, I'm starting with this 50 because that's the volume that I know. So I'm having to travel from the smaller to the larger, which tells me it's this arrow. So I'm multiplying by the scale factor. And the scale factor that I'm multiplying by is, because it's a volume, it's the volume scale factor. So it's 27/8. And that is actually going to give me an answer of 168.75 centimetres cubed. Okay. Looking at my second example, doesn't say similar anywhere in it, but what we have is we have two spheres. Spheres are like cubes. They are similar just by virtue of their shapes. So we've got that they have to be similar. They're made of the same material. That is also very important. If they're made of the same material, then the material has the same density. And we can actually say that the ratio of the weights, apologies for the camera moving, the ratio of the weights is equal to the ratio of the volumes. So we've got it's the same material. So therefore we've got the ratio of the weights is going to be equal to the ratio of the volumes. So at this point I would draw myself two very rough little spheres. I'll stick with the same colour. So we have our smaller sphere and our larger sphere. They don't have to look three-dimensional. It's really about getting the information from the question onto something so that you can visualise it and you can solve it easier. We have that the smaller one has a weight of 32 kilograms. The larger one has a weight of 108 kilograms. We know that they're similar, so we know that to go from the smaller one to the larger one, we multiply by the scale factor. From the larger one to the smaller one, we divide by the scale factor. We also know that the radius of the larger sphere is 9 centimetres. And then we have to think, right, okay, which scale factor do I know? Well, if you look at it, the thing that we have two pieces of information about is the weight. So we can say that the volume scale factor, because remember that it's equal to the weight scale factor or the ratio of the weights, The volume scale factor is going to be 108 over 32, which is 27 over 8. That allows me to say, therefore, that the length or the linear scale factor is the cube root of that. So it's 27 over 8. Remember again, if you're cube rooting a fraction, you cube root the numerator and cube root the denominator separately. It's going back to your indices. So we've got 3 over 2. So therefore, our smaller radius is going to be, we know the larger radius is 9. We're travelling in this direction from the larger to the smaller, so we divide by the scale factor. In this case, because it's a length we're dealing with, it's the length scale factor. So we do 9 divided by 3 over 2, which is the same thing as 9 times 2/3, which is going to give us 6 centimetres. Okay, it's about thinking about what scale factors you know, linking your scale factors together, whether it's working from an area to a volume scale factor, from a volume to a length scale factor, it doesn't matter. Link your scale factors together and use the correct one.